just begin the last talk of this day. This is the talk by a representative of our sponsor, Samsung Electronics Polska, and it will be Urszula Oleszek, which will present the talk, Do we need deep learning for recognizing phrases in natural language? So please begin.
Thank you. So, as Łukasz said, I am Urszula Oleszek. The short version of my name is Ula, so you can call me Ula. I'm here and I'm just a presenter for today. I'm on behalf of my friends, my colleagues from Samsung company. And today I would like to talk less or more about deep learning and classical architectures to recognize phrases in natural language. So nowadays we live on the world where everyone has got a phone. We produce a lot of textual data, and we also can extract a lot of information from this data. So how can we do this? We can recognize phrases by a method which we call sequence labeling. So what exactly is the sequence labeling about? Generally, we can think about the sequence of tokens, which we can name by the big X, and we would like to achieve, as a result, the sequence of kind of labels, whatever the labels would be. And we represent our vector of labels by big Y. So, in the textual data, in this particular example of sequence labeling, we have a sentence where every word is represented by one token. So we've got 8 words in this sentence as follows 8 tokens. And the task we would like to model by sequence labeling is to label each word with part of speech tag. So in this example we see that she is pronoun, Bob is verb, and so on and so on. How can we construct the model? Basically, we can model this situation by conditional probability. So we can calculate conditional probability of sequence of our output labels given sequence of our incoming tokens. So in this example, we have some set of labels, and for every token we will compute the probability of each token. And how could we decide which label is the best? We will take the label with a maximum probability. But as we can see, a lot of information could be encoded also in labels itself. In this approach, we take into account only our incoming tokens, not our output labels. For example, some part of speech tags cannot precede or follow each other. So sometimes it is important in this task to, if we want to compute optimal output label sequences, we should take into account not only our input, but also possible output labels. And as we can see here in this example, in most of natural languages, like in English language, especially for languages which are positional, the same word can act as a different part of speech. So here in this sentence, I am swimming, the word swimming act as a verb, while in the second sentence, she has swimming eyes, the same word swimming act as an adjective. And we cannot know which label is the best if we take into account only our incoming tokens. So to know which one occurred in a specific sentence, in a specific example, we should look at neighboring part-of-speech labels, our output labels. So the conclusion would be that our neighboring part-of-speech should affect significantly the probability of our token's part-of-speech tags. The part-of-speech tagging is not the only one example of sequence labeling. Other tasks, very important from the business perspective, are sentiment analysis and named entity recognition. So what is exactly the named entity recognition? We would like to recognize some named entities. And by the named entity is we understand the real object, like person, localization, place, product, etc. This named entity can be marked by a specific name, also can be abstract or real. Like by real, I mean physically present in the world. And examples can be Barack Obama, New York, Volkswagen Golf. So in this example, this is our sentence from the previous slide. She bought yesterday a new Samsung Galaxy S7 Edge. So the information we would like to extract from this sentence is here, Samsung Galaxy S7 Edge, and this is the named entity product. And if we have a lot of textual data, it is very inefficient to do such a task without computation. The second task is sentiment analysis, which is basically the automatic analysis of emotional states or subjective feelings about something. And this method is very common. For example, it is used in opinion poll or for summarize surveys results or for market analysis. And here we've got two examples of what exactly the sentiment analysis is about. In first sentence, I don't like winter, it could be warm already. We can see that by this phrase, we annotate this sentence with the negative sentiment, whether in the second sentence, I love the season when everything blossoms. By tokens I love, we see that the sentiment is positive. As you can see here, each of also for named entities or sentiment, positive and negative, we extracted not only one token, but basically more than one token. And here you can see that each token separately, I don't like, may have a different meaning. For example, the word like separately has a positive sentiment, whether we need to add the negation to obtain the negative sentiment. So, what kind of methods we use to sequence labeling task? The first natural method we can use is the conditional random fields method. So, from the beginning, this method, label probability, is calculated independently, and this is a very important step based on the context. And the specific part of conditional random fields method is to modify independently calculated probability by sequence of labels. Other methods we can adapt to this task are deep neural networks like recurrent neural networks, LSTM and GRU. And here, labels prediction based on two elements. The first is a current our input, the incoming token. And the second element is the memory of previously loaded inputs, which we transfer, I will show you in the next slide. And here we've got currently state-of-the-art architecture for sequence labeling task. This method, merging those two approaches, conditional random fields and neural networks, In the next slide, I will show you more detailed what about is the state-of-the-art architecture. So, starting from the beginning, how can we predict our labels by independent calculation? So basically, we tokenize our sentence, and each token we transfer separately to our model. And here we've got the final layer. Here is the softmax layer, and after passing this layer, we obtain the conditional but separately calculated probability of label given input. So by this calculation, we obtain kind of matrix. You can see this matrix here. And for example, in the rows, we have each of our label. Here I'm showing the task of part of speech tagging. So as our labels, we've got here part of speech tags. And in the columns, we've got our incoming tokens. And as you can see here, for each token and for each label, we obtain kind of number, which we interpret as a probability, as a conditional probability. So by the independent calculation, our model would not exactly know which label should be the best here for our word swimming. And as you can see here, the probability for the label adjective is higher than for the label verb, which we know that should be here. But what can we do? We can calculate the total distribution of anticipated labels. And this is the moment, this is something which is done by the conditional random fields method. So we do not calculate separately every probability, but we calculate the total distribution. So we put here total whole label probability given whole incoming input. And by this step, we transfer the information about previous input. So with this approach, we can increase probability for right label. And yeah, okay, we will try to do it. The basic example of conditional, we are still in the conditional random field method. And the basic example, the most basic of conditional random fields is the linear chain conditional random fields method. So here we've got the independent calculation of output labels. So if we want to calculate the conditional probability of whole sequence of our labels given whole sequence of our inputs, because we calculate it independently, we can do something like this. So we can write the product of each probability for each label given each separately input. And here we've got the calculation of our softmax layer. And because the product of exponential is the exponential of sum, we can easily write something like this. So here we've got the probability of label yk given every input y xk. So this is the independent calculation of our output labels. And what is doing by conditional random fields? We simply modify our independent calculated probabilities by a specific matrix. In this matrix, we've got the information about how our model like to our label yk plus 1 be preceded by label yk. So this is the way to transfer the information about, let's set here, the total distribution, the information between our labels. So other methods to do sequence labeling tasks are neural networks, and how they do this. In each cell, we've got incoming input, and in each cell we also got the hidden layer. And the information about our labels is transferred from one cell to another by transferring the hidden state. But we've got some problems with this approach because this kind of networks tend to decrease the transfer of information very, very fast. So in 1997, 20 years ago, there were introduced special architecture which we call long short-term memory LSTM in short version. And this architecture was created especially for long dependencies because it has got the special additional cell state which we call the gates forget. So the neural network can learn what to remember and what to forget. So it can transfer the important information on long dependencies than the classical approaches. And here you've got the last year published absolutely state-of-the-art architecture for a sequence labeling task. And in this architecture, we've got the classical conditional random fields method merged with neural part, which is exactly the long short-term memory neural network. So basically, at the first step, we calculate the probabilities from the by the LSTM architecture. So we obtain the matrix with probabilities of our labels for each token. Next, we transfer it to the conditional random fields method only to modify those probabilities with our information about labels. And finally, we use the dynamic Viterbi algorithm to decide which label is the best. So this slide is to show only that we simply check this part from the softmax layer with the LSTM, and the modification of our final matrix is the same. So this is exactly what the conditional random fields method does.
May I interrupt you?
Yes.
What was the model in this L+1 that was a perceptron with just a single softmax layer?
Yes.
Okay.
Exactly. The final softmax layer. Okay. So yeah. Let's see inside this state-of-the-art architecture. Because I said that we've got the hybrid of long short-term memory neural network and conditional random fields. But if you want to look a little closer, we've got exactly 4 separate long short-term memory neural networks here. And from the beginning, we do something which we call by run long short-term memory architectures forward and backward, but on characters. So in this step, we would like to extract information which is in subword information. Then we do the concatenation and dropout. Next, we run LSTM forward and backward, but on the worst level, so this is the level higher. We do concatenation. We transfer this in this way obtained matrix to the hidden layer. Then, as a final layer, we've got the hyperbolic tangents layer. And here is exactly the moment when we modify our probabilities by the conditional random field matrix. And basically, we've got the Viterbi algorithm to take a final decision. And here we've got only to make our intuition some statistics about COM 2003 named entity data. So this is the statistics of corpus, which is very well annotated and which we normally used to named entity tasks. And this is kind of medium size of corpus. By corpus, I mean the set of documents with annotated named entities. So, as you can see, for English data in the training set, we've got close to 1,000 articles. And for development and test set, we've got close to 100 articles. And as I said, it's a medium size. So we performed two experiments, and to understand what exactly we wanted to show you by this this figure. I need to tell a little about why we wanted to validate the noise effect on our models. So imagine that you have 3 or more models trained with different parameters, and you would like to test if the model is good or not. So something which you would need to have is the corpus. So this is the set of documents with annotations. But from the nature of a natural language is ambiguity. So the annotation made by linguists may not be easy. Those two tasks, sentiment analysis and named entity recognition, are really hard because, for example, if you have a White House in your data set, you don't know if you are talking about White House in the Washington or if this is White House, just a random house with a color of white. So, because of the ambiguity of the language, normally to produce good quality corpus, reference corpus, we ask to do annotations more than one person. It would be 3, 4 or more linguists. And after their work, we calculate something which is named annotation agreement, annotators agreement. So we just wanted to know what would be the impact of noise in the annotation on our validation of model. So we defined three types of noise. The first one is deletion of n% true annotations. So in this case, part of existing annotations preserved in here in this step, and this type of noise is marked as blue one. The second one was addition of n% new annotations, and in this step we did not remove existing annotations, and this kind of noise is marked as green one. And the third was the constitution of both A and B, and we marked it as a red one. So here you've got the results for task of sentiment analysis. Here is corpus multi-perspective question answering, and state-of-the-art architecture neural conditional random fields method, and here is classical conditional random fields method without the LSTM part. Here we've got results for named entity recognition. So we've got COM 2003 corpus, and also state-of-the-art architecture and classical conditional random field architecture. So we were absolutely surprised because of these results. As you can see here, we've got here the noise level. So here you see that the performance of this state-of-the-art architecture is more than 80%, even if we have close to half of the data with noise. We didn't expect such a result, and also for 10% or 20% the behavior was the same. Also, as you can see, the performance of tasks for sentiment analysis is lower than for named entity recognition. This may be because for first, sentiment analysis is a really hard task, and the annotators' agreement for this corpus was really low. So, as you can see here, the neural, the state-of-the-art architecture with neural part, with deep part, has got the performance close 10% higher, bigger than the classical conditional random field model. And believe me, it's absolutely really big difference. Okay.
Can I ask a question?
Yes, of course.
I'm mystified by the fact that in some cases it seems that noise seems to improve a bit over the conditions without noise.
That's a great question. I hope that someone will see this. So here, as you can see, we've got here this this line shows us the score without noise, and when we added the noise B, where there is addition of n% new annotations, as you can maybe see here, the performance is a little bigger than the score without noise. So, do you have any idea why? No? Well, I think that when you write here, we did not remove existing annotations. We only added new ones, randomly. So probably we added something which was missed by annotators.
It might also be due to better regularization of the whole thing, because
maybe, yeah.
With named entity recognition, it's a lot about generalization of the scheme, and noise helps with that, and is often used for this in some way, so that might be a defect.
Yeah, that could be the another explanation. But firstly we did a lot of research to find some results on the noise effect on the performance, noise effect in the context of annotation, to our model performance. So we wanted to show you this, maybe you would like to follow this kind of research, because quite new. We don't know if the behavior will be the same for other architectures. It's only under the research. So,
Excuse me.
Yeah.
Can I ask another question? So, do you have the result only for the neural deep learning without CRF? Did you compare that?
Here we've got.
Yeah, that's only for CRF.
Mm-hmm.
But you have CRF and
Mm-hmm.
deep learning and its conjunction, right?
Yes.
And so, do you have the result only for the deep learning?
No, because to obtain 1 point, it takes close to 1 week time. Yes, because we need to prepare the data, train the model, use the resources, by which I mean our servers. And we have a lot of different tasks to use our servers. So this is why we wanted to interest you on this kind of research.
Yeah, but if you don't have that, CRF might not be working when used with the deep learning, right?
Without the deep learning part.
So the point of this talk, one of the point of this talk is that you use the deep learning plus CRF, right? And in order, I understood that the conjunction is better than the CRF, but you also have to show that this conjunction, in order to show that this conjunction is working, you have to show that NCRF is doing better than the simple N, neural.
Okay, I understand what you mean. Yeah, maybe, that's a good point.
Or maybe you don't have the difference, then the conjunction wouldn't mean anything.
Yeah, that's a great idea to do more research.
Okay.
Thank you. Thank you. Okay, so here we've got the comparison this is all for named entity recognition made on COM 2003 corpus, and here we do some tuning on classical conditional random field model. And here you've got two architectures, deep learning architectures. So, is the performance really different? The difference is huge? Well, it is indeed, but close to 3 points of F1 score. So, as you can see here, deep learning achieved better results, whether the classical architecture, while under the tuning of the server features, may have still absolutely great performance on the named entity recognition task.
Can I ask a question? Do you remember more or less how many entities there were in the task?
How many entities? How many classes? Or
Yeah, how many instances to be classified?
do you remember how many classes?
Excuse me?
Do you remember how many classes were in this named entity recognition task? I think that it was close to 4. Yeah, because it was. I said that it was done on COM 2003. So the classes you've got here is the location, organization, person, and everything which was marked as a named entity, but was not location or organization or person.
I was just wondering whether that very small difference in performance could be actually pinned down to the actual examples that are misclassified in the conditional random fields, just to see whether there is something in common among the things that the classical methods don't pick up. I don't know.
Yeah, maybe. I don't know too.
How many hidden layers were you using for the deep learning method?
How many layers?
How many layers?
As I remember, it was close to 2 or 4, but
2 or 4. It can make a big difference, right?
yeah.
In terms of the kind of representations that you can learn or represent something.
Unfortunately, I
Yeah.
can't answer this question now.
This came after seeing that there is a small difference between the.
Yeah.
It might be. About the size? What kind of, what's the number of neurons? Do you remember?
That is 100.
100?
Each layer.
100 in each layer. But you don't remember the number of layers?
I don't know. What do you mean by number of layers? We just one GU cell, which consists of like 9 layers.
9 layers.
Yeah, if you take a look at the GU cell, it's a bit slightly less, a bit more simple than LSTM, which has 12.
But as I said before, in the neural conditional random field we use 4 LSTMs and each one has 9 layers. So, yeah. Okay, so to take a short summary, a conditional random field method after the appropriate feature tuning, and by the feature tuning you can understand the part of speech tags, morphological forms of words, subword level features. The results are really competitive. Classical neural networks architectures are quite fast, especially when we use the moderate size of embeddings. And the hybrid method of conditional random fields and LSTM neural networks is the currently state-of-the-art architecture, and it is surprisingly resistant to noise effect. So to answer the question, do we need deep learning for this task? If you have noisy data, probably yes, and probably this is the best architecture. If you got a lot of data and you don't know what kind of features you can add, or you don't want to do this, maybe yes, but maybe not in every case, because by the appropriate feature tuning you can obtain quite competitive results with the classical models. So yeah, the best part. Yeah, but why I just want to talk about this. We've got R&D research and development centers around the world, not only in Europe. And the sequence labeling task is something what I could to talk about, and what I'm working about, because I'm working on the text analysis, natural language text analysis. But if you are interested in big data analysis or any artificial intelligence solutions, yes, we are looking for example, passionate hobbyist programmer. And yes, as you can see here, it's not only natural language processing, but also computer vision, or machine learning itself, or deep learning, or big data. So we're looking for data analysts or natural language processing engineers. And well, I'm honored to be here with you. And from my perspective of my education, because I'm a physicist, and my perspective as natural language processing engineer, your work is absolutely significantly important to our work for industry. So thank you to be here. Thank you to working on statistical approaches in the natural language. And as a representative of Samsung company, yes, we need your results. So thank you. Let's go.
Yes, so would you like to ask some question? Okay. Yes,
yeah, thank you for the motivating words. It's nice. Maybe some of us are too old, but cool to know that at least our students have a future.
Yes, exactly. They have.
But I have a question also. We heard in the last talk that English is a very rare language, and Polish is a very difficult language in some sense, and the world has many languages. So can you comment how are the results for Korean or Polish or other languages, or what are the differences of the state of the art in English to other languages?
Well, I'm now wondering what I can say, but if I would like to comment, well, we do these artificial intelligence systems, especially for those languages which are very common because of the business purposes. So English is the most common language in the world, and for example, the Spanish language. And what is the performance on Polish language? I really don't know, but from being a native Polish language speaker, I suppose that the tasks would be crazy difficult. And what about Korean? Korean language is quite different than English language, although I really don't know what are the this kind of results.
But you expect that there are significant changes in the methods, or it is just...
Yes, especially in the part of speech tagging. So for example, for languages like Korean or Japanese, we use conditional random fields method.
But for us,
for part of switch.
word tokenization.
Yeah, exactly, and for word tokenization. So basically, we will need to change kind of parts of our models, and yeah.
You got me with the stable employment part. That's another thing.
Yeah.
So I have a brief question. When you presented the CRF, the second term on the probabilities was the probabilities on the labels that were adjacent.
Here?
Yeah, exactly. So why to stop there? Because you don't have a problem with data sparsity, right? You could actually take larger n-grams, and you would expect that would. My naive expectation would be that that would have a very important impact on the classification. Does that make sense, or?
Yeah, it's sometimes done in graph. Not that so. Go backwards more than just one.
I suggest if you include higher order interactions, the computational time increases significantly.
So you say the gain is not so much as to justify.
It's also diminishing benefits. So you get an improvement, but probably the improvement is not working.
Well, mentioning that the cross-linguistic stuff, for instance, in languages that have a smaller number of labels, for instance, think about Mandarin Chinese, then I would expect that you have to move a bit forward because the statistics won't be that interesting in that respect. It won't help you to distinguish a lot of the local contexts.
So my question is, so you don't work on Polish in the Polish department or something?
Yes. Well, I can do this after hours.
Okay. Do you have some more questions? Okay, so let's finish.
Thank